Welcome to solverfy.
This is the answer to Chapter 15, problem number 64 from the Smith Organic Chemistry textbook. This problem is asking us to synthesize 5 different molecules, starting only from ethane, and then using any reagents that we need. A, as the problem indicates, we'll start with ethane. We'll do a free radical bromination to get to ethyl bromide, bromoethane, whichever you want to call it. And then remember that when we have an alkyl halide, a useful way to convert that to a species to which we can do much more diverse chemistry is to treat it with potassium tert butoxide and get to the alkene. And so that's what we do here to get to ethene. And then we can dibrominate that to get the dibromide species. And then remember, one equivalent of sodium amide will do one elimination reaction. Two equivalents of sodium amide will do a double elimination reaction. So that's what we're able to do. And that gets us to ethylene. And that is the molecule that we were asked to make for A. And so that's A. So then for B, we can start with our product from A, ethylene. And remember, with an alkyne, a terminal alkyne, if you treat it with sodium hydride, you're going to remove one of the hydrogens and make a carbon nucleophile. So that's what we do here. Then we can use the bromoethane that we made as our first intermediate from part A, and we can add them together. And we'll get our target molecule for B. And so remember, for these problems, it is fair to use anything that you've made before. So our only requirement was that everything that we use, all the carbons that we use, come from ethane. And so starting from the product for A, and then using this intermediate also from A, they both originated from ethane, so they're both fair reagents to use. And throughout the rest of these problems, you'll see that we do start with intermediates or products from earlier parts of the problem. So again, for C, we're going to start from an intermediate from A, ethene. We'll do an MCPBA epoxidation to get to the epoxide here. And then we'll use this nucleophilic carbon species that we made in B, the first intermediate from B, and then follow that with some water. And that's going to give us this alkyne alcohol that we were asked to make. And so that's C. So then for D, we're going to start again with an intermediate from B, actually the final product from B. We'll treat that with sodium hydride. And again, like we said earlier, that's going to make a terminal alkyne into a carbon nucleophile. So that's what it does here. We use this same ethyl bromide species that we made as our first intermediate in A, and just add them together. And we get the 6-carbon chain that we're looking for, but we have an alkyne in the middle. So if you remember back to an earlier chapter, your dissolving metal reduction, sodium in liquid ammonia, is going to give you trans selectivity in reducing an alkyne to an alkene. And that's what we want here. We want the trans product, and that's what we get, and that's D. And then lastly, for E, we're going to start with this the last intermediate from D, the second to last molecule before the product. And we will very simply treat that intermediate with some sulfuric acid and water and some mercury sulfate. And that, if you remember from an earlier chapter, is going to convert that alkyne to a ketone at the position that the alkyne was. So really, it would be a mixture of the 2 carbons of the alkyne that would get the ketone. But since this molecule has a plane of symmetry between those 2 carbons, either one is going to give us this exact same product. So it doesn't really matter. It works for this reaction. But do bear in mind that if one of the sides was different from the other side, we would get a mixture of products here. But this time we don't. This time it's fine. And so that is the answer to chapter 15, problem number 64.